All right, wonderful. So good morning, everyone. We're now in the third seminar of this SMAC series. And the series is meant to be a brief introduction in the form of a live demonstration of software tools that we think can be particularly useful for research. Always thinking about astronomy mainly. And today we'll have a seminar about Gnuastro tools, which is an open source suite of command line utilities that are particularly useful for astronomy and astrophysics research. And the speakers will be Mohammad Akhlaghi, who is here a postdoc at the IC and is the main developer of the GNU Astro tools, and two students that work, that do research in galaxies, Raúl Infante and Joseph Putko. The format will try to keep it within an hour, and but the questions may go over time. So people should feel free to connect or disconnect at will. And we'll try in the question section to go and manage the questions through the chat, or you can raise hands or say through the chat that you're interested in asking a question, and we'll try to moderate it. Let's see how it works. And please try to keep your cameras on and microphones off while you're not speaking. Mohammad, please.
Yes, thank you very much, Carlos, for the great introduction. Thank you very much, everyone, for coming. So yeah, as Carlos mentioned, today we'll focus on Gnuastro. So let me just share my screen. So you just give a basic introduction before we go into the actual the actual commands and how to run them. Okay, so GNU Astronomy utilities. Well, it's as you see, this is the main webpage. You can just find it in GNU, the main page of GNU. And as I explained in the first session, GNU has been a core component of free and open source software for the last 40 years almost. And yeah, so that was why during my PhD, when I actually started this project, I submitted my code to them, and they refereed it, actually, very much like an academic referee process. They refereed it and into the code. It wasn't just, the paper. It actually took longer than the paper to get refereed. Yeah, because they actually done the code and everything. They went into the code and done some very detailed checkings. Okay, so it's a large set of programs, and I'll just click over here. You can see the name of the programs. This is from the documentation, and it has a very complete documentation. So we're going to review most of these programs today. And for example, if you want to just see the documentation, you can go to the Gnuastro webpage. There's a documentation part. And for example, in PDF, you can see the whole documentation there. It's available. Yeah, I just made the most recent release, version 12, a few days ago. So far, you see many people have started to contribute, and this number is growing. I'm really proud. We're getting a large community of people contributing. And yeah, you see it's very complete. So it's a large set of programs. It has some tutorials that you can already get started, and that's where we got these commands today from. So I really recommend you to go through the tutorials. There's there's a lot of written explanation. And yeah, there's programs for containering, data containers, for example, playing with FITS files, tables, for manipulating data, like convolving them, adding, subtracting, warping, and doing data analysis, detecting, segmentation, making a catalog, matching catalog, making profiles, making noise, and even cosmological calculations now, because mostly my field is galaxy evolution. This is here. But yeah, and as more people are contributing, it's getting larger and larger. So to play with Gnuastro today, we are going to use the Abyss data set. So it's a survey by the Hubble Space Telescope. Well, it's a long survey. It's like a 20-year that they've taken data from 20 years of observations almost of HST, and they've stacked the images together to make a really deep, technically it's the deepest image we have of the universe, right? And so this is like a snapshot of the full field of view. And so what makes this IAC Abyss survey so unique is that compared to the standard release, so over here on the right, you can see the standard release. And over here on the left, you can see the IAC release. So for example, do you see around this bright galaxy here, there's a lot of low regions, like, dark blue regions, and around this bright galaxy as well. This is because in the standard reduction pipeline, they've done not a good job at subtracting around the galaxies. But in the ABIS survey, which was done by one of the PhD students here at IAC, Alejandro Borlaf, and our team here. So Alejandro actually done a really nice job using some of Gnuastro tools to actually remove this over-subtracted halo. And he called this paper really nicely, the missing light of the Hubble deep field. So he was actually able to show that there's much more light, much more data, much more knowledge in this data set than what the standard reduction has given. And okay, so we're going to play with this data set, and Raúl is going to start with Gnuastro. So I'll just stop sharing screen here, if I can find my Zoom. And yes, okay, it's up there. And Raúl can continue.
Okay, thank you, Mohammad, for the nice introduction. So as Mohammad has said, we are going to play a bit with some of the program of Gnuastro, using the data from ABIS survey. So let me stop sharing my camera. Okay, that's it. So let's start by downloading the data. So let's do here. So you can see my screen, right? So I will do here a directory called download. So this is something that I have already done. And we are going to download the data. So we are going to use the program curl here, just specify the name of the image. So in that directory, I'm going to put this with this name, okay? And then I will specify the URL from which I'm going to download the data. So that's it. So that command will download this this image, which is the filter F160. So this is something that I have already done. If you would like to download all the different images that we have for this particular survey, we can make a loop using the different filter labels. So for example, for F in the different filter labels that we can use. So I will paste this. I'm missing here an F, okay? So for this set of filters, do the following. Okay. Essentially, I'm going to use this command, basically, to download all the different data. So if I paste here, and then I will have to change the filter, okay? Here and here. And with this command, it will download all the different images for the different filters, okay? So this is something that I have already done. I am going just to use one of them. So I will copy from this directory, this image to the other one, okay? So that's it. I have here two directories, ls download. Here I have, I will remove the other one. So just to be clean. Okay, so we are going to play with this image. As Mohammad has said, we are going to play with Gnuastro program. So all programs of Gnuastro, is it possible to use from the command line, and you have just to type in the command line AST and press tab 2 times to see all the different programs that are available to use from the command line. So the first one that we are going to use is AST feeds, okay, this program, and that this program is very useful for extracting some data from the astronomical images. For example, if we do the following, download and the image, it will show us the image, okay? How many extension the image has. So for example, it has in the first extension just some information. In the second, we have the science image with this data type and with this dimension. And then we have another two extensions with different data. So instead of having a look at the skeleton of the image, let's say we can have a look at the header of each particular extension. For example, we can say AST feeds, then the name of the image, and then --HDU equal to 0 to see the content of the header of the first header of that image. Okay? If we want to see the content of the first header, so the second one, it will be different. This is from the science image. Okay, it is possible to use another way. So, for example, just typing here -H1, which is shorter, it will do exactly the same. Okay. Then we can remember from the previous talk, we can pipe this result into another program head just to have a look at the first 20 lines and not showing all the information. This is going to show us only the first 20 lines, okay? So the result of the header is piped into this program to see only the first 20 lines. Okay, now imagine, for example, that we are interested in getting some keywords from the header, okay? So for example, we can pipe the header into grep to look for any particular keyword. For example, we are going to look for the keyword CDELT1, okay, which is the pixel scale of the image. You can see that this value, so this keyword is found, and this is the value. Okay, so this is the pixel scales in unit of degree per pixel. Okay, so if we now want to select not the whole line, so this line, but the actual value of this keyword, we can use awk. Okay, so in the same way here we can use awk. Remember the previous talk. So we can type this. So all lines starting with CDELT1, which is the keyword. Okay, and then from this we are going to print only the third column. So this is the column number 1, this is the column number 2, and this is the column number 3. Okay, so here number 3, that will give to you the value of this keyword. This is in unit of degree per pixel. If we want to operate with this just to showing arc seconds per pixel, we can multiply the value here by 3600, and you will obtain the pixel scale of this image in arc seconds per pixel. Okay, so this is very useful when taking data from the command line, directly from the command line. So not only, so it is not possible only to get data, but we can actually modify the content of some data. So for example, if we look for AST feeds, okay, the image, and we want to change some values, for example, let's have a look at the keyword PC, okay. Okay, I miss here the extension, so H1. We can see that this value, PC, this keyword has this value. But in this particular case, this is a floating point error, okay? So anyway, imagine that, for example, you want to remove this particular keyword, this and this. So you can use AST feeds with the option --delete. And then specify the keyword that you want to delete. Okay, PC1, 2, and we also want to remove the other one. Delete PC2, 1. And that's it. Just with this command, we have removed these two different keywords from the original image. If we do again the same command, now we see that these two lines are not appearing here because we have removed this. Okay, this is just for removing, but of course you can also modify the values and the keywords, okay? So now let's have a look at the image with DS9, just to have some feeling of the data, download and the image that will open Windows here. Okay, have to move. And you can see here the image itself. Okay, so we have so many objects, the background, and so on. So DS9 can allow to get some parameters from the command line. So we can select here, for example, the scale, set scale, and then fit the size of the image to the windows. So we can say zoom to fit, just to open the image directly in set scale and fit to the size of the windows. Okay. Okay. So now let's consider that, for example, we want to extract, so to select one particular region of our image, for example, centered in a given galaxy that we want to study. Okay, so we have to use the program AST crop. Okay, and then we will specify the image, and then we are going to specify the center of the galaxy in which we are interested to crop the image in pixels. So we have to select here mode equal to image and then the center. So we are going to consider the center in pixels 1603 in the X direction and then 1316 in the Y direction, and then we have to specify the width. Okay, so width in pixels also. So in the, for example, we will give 500 and 200 pixels, and that's it. By default, AST crop has created this image, which is a smaller image centered in that pixels with that dimension. Okay, if we have a look at this particular image, we can see that the first extension has no data, while in the second extension we have the data itself. So let's have a look to verify that this is the case. And here we can see that this image is the one that we want. Okay, so here is the galaxy in the coordinates in pixels that we have selected. But now imagine that we don't want to use pixels, but for example, we have some particular catalog that we want to use, and catalogs in general use WCS. So we have to specify here WCS, and again the center, and then I will paste the center of the galaxy in WCS. So right ascension and declination here, and then I have to specify the width again, and the width has to be specified in the same units that the units of the header. Okay, so in this case, we have to put, for example, 0.01 degree, because the units are in degree per pixel, but we are going to use another option. We are going to say we want to crop the image with a size of 20 arc seconds, and then we have to divide 20 arc seconds by 3,600, because this is the how many arc seconds have 1 degree. Okay, so we have to put, we can put here the output with another name, my galaxy.fits, and that will crop the image with a new name. So now if we have a look, DS9 my galaxy, we will see that we have done the same, but using world coordinates. Okay, around the galaxy, and in this case, since I have specified only one size, the size along the two directions are exactly the same, 20 arc seconds. So let's move to another very interesting program, which is Chisel. So let's remove here all the images that fits. And now imagine, for example, that we want to obtain a catalog from this particular image. Okay? So the first thing that we have to do is to detect the signal of this image. We have to separate the signal from the noise. And to do that, we are going to use AST noise chisel. AST noise chisel. And then we have to specify the input image, which is download and that image. And then, for example, the name noise chisel.fix. Okay, so noise chisel is going to convolve and it's going to do many things in order to separate the signal of that image from the noise. Here you are. So we have this image. We can have a look with AST feeds to see the content, and you will see that we have different extensions. The first one has the parameters of noise chisel. The second one is the input image without the sky background. The third extension is the detection, so the maps of the detected signal. And then we have the sky and the sky standard deviation. If we have a look with DS9, we can open the different extension with the option here, multi-extension view, noise chisel image. And we will see, yeah, let me move the image here. Okay, and then the different extension. So we have here the original image without the sky background that the noise chisel has model, okay? And then in the next extension, we have the mask, the signal. So here we have with pixel values equal to 1, all the signal that noise chisel has detected. And the noise has pixel values of 0. So if we make a blink between the two different images, you can see that all objects has been detected and classified as a signal. Okay, so now, for example, now that you have detected all the signal, imagine, for example, that you want to mask all the different, so all the signal into that image and let in the image only the sky background, the noise. Okay, so we can use here another nice program, which is AST arithmetic, which is for making some operation between images. So we have to specify here the input image. So we want to mask from this image all this detected signal. So the detected signal is in the same image, but in the second extension. Okay, and we have to put none where, okay, where the mask is equal to none. Okay, I will put here the output, for example, only sky fits, and I'm missing here the operator equal. No, it's not necessary to put here. So that's it. So we have masked this input image using this mask image, putting nuns where the mask is equal to 1. Okay, so just have a look. We can have a look to that particular image, and you will see that now we only have the sky background. Okay, all the detected signal has been put with none, and we are having here only the sky background. In the same way, we can do the other operation. So instead of masking the detected signal, we can say that we want to mask the sky background. Okay, so we can put here detected. Okay, and here we have to put the other operation, the other way, not. Okay, and that's it. If we have a look, we will see. I spell the name. Okay, and here we can see that now what the pixel that has been masked are the sky background, the noise. Okay, so the objects are not masked here. Maybe if I change the color, it is more clear. Okay, so all the noise has been masked with none values. So this is really useful when you want to mask different objects and different region of this of the images. So now we are going. So now we only have an image which is 0 for the noise and 1 for the signal, but in principle we would like to use that mask to split the different signal into different objects, and that can be done with the program AST segment, which is going to segment the different signal into objects. So we have to put here the noise chisel output. So this is the input for segment, which is the output of noise chisel. And then, for example, specify the name, seg.fits. And this program is going to segment the signal into different objects. Just having a look at this, this image with AST fits, we can see that now again we have some parameters in the first extension, the input data, clamps, and objects. So if we with DS9 and the option view, we can have a look just to see that now the different extensions are not zeros and ones for the signal, but okay, let me set scale. So now, for example, the clamps is different. So you can see now that the clamps are peaks above the noise of the image. So maybe changing the color, you can see that if I make a blink, okay, you can see that all the detected signal now has been segmented into different group of pixels. Okay, so now this image is going to be used with another program, but in this case, Mohammad is going to tell us how to use Make Catalog and other different programs to make data analysis. So I will give to you the control, Mohammad.
Thank you very much, Raúl.
Okay, thank you.
Yeah, so if you just,
Okay.
yes, great. Okay, so I'll just activate my share. Okay, so we'll continue with where Raúl left off. So as Raúl was saying, we found the detections and we found the clumps in those detections, right? So so now it's time to actually make a catalog from those detections and get into our higher level science. Now this particular case is like a deep galaxy image, but it's the same for like star clusters or in galaxy physics or even solar system physics, because the wings of galaxies from a signal to noise point of view, they're identical like with the tail of a comet. So this is very general. And you can use all of these. So for all aspects of image processing, even some biologists have recently started to use it for doing their analysis. So this is very general. Even though we're using a galaxy image, please have in mind these concepts can go far beyond galaxy studies. It's just the general image processing. Okay, so we have the segmentation map that Raúl just made, and we can actually have a look at it. So we can say ds9 seg.fits. And here you go, we see that same image that Raúl was showing, and you can see the clumps that Raúl was just explaining, and the objects. Okay, so now we want a catalog from all of these, right? So we want to know how many objects there are, what's their brightness, what's their color, and so on, right? All the science we want to make. So there's this other program called AST Make Catalog, right? So Make Catalog, as the name says, its job is to make a catalog. So it takes the labeled images and it takes the labeled image, it takes the values image that you want, and it does measurements over each individual label for your job. And it does it in parallel. So it's like, yeah, it's really fast. And you'll see now. So we give it the output of segment, and well, we ask for columns. We say, okay, what do I want? I want the ID of the objects. I want the RA. I want the deck. I want the magnitude. I want the signal to noise. I want the axis ratio, for example. And okay, you can also give it like basic information about your image so it measures properly. For example, you want to give it the 0 point, and the 0 point in this case is 25.94. You can look it up in the webpage. And okay, we also want the clump scat. So we want both the object and the clumps. And finally, we can write the output. So we say output is catalog.fits, right? Okay, do you see? Finished. This image was like, how big? It was like 3,000 AST fits. We can actually have a look. Seg.fits. This image is almost 3,000 by 3,000 pixels, and on this tiny computer of mine, you see done it in 0.2 seconds. Done all the measurements on both images, catalogs and things. So let's have a look. So you do AST fits. Well, we asked for a catalog.fits, right? So you see, it actually makes two extensions, one catalog for objects and one catalog for clumps. So yeah, so these are the things that it has, and you can actually all of the Gnuastro programs, as Raúl was just showing, their first extension is the configuration files that went into the program. And this is great for reproducibility, because like in 1 month or 2 months that you've shared the data set with someone else, you may have lost your command, you know, the command that you used to run this program. So you just do -H0 here, as if it's, you actually see, for example, you see the 0 point that we gave it is actually stored in the header. And like, well, if you wanted sigma clipping or like upper sigma, upper limit measurements or things like that, all of the parameters that make catalog or noise chisel or all of the Gnuastro's programs use, this metadata is written in the 0th in the first extension, and the actual data is always written in the next extension. So if we go back, okay, let's have a look at the objects table. Okay, so this, you see the objects table is a binary table, and it's 2,274 rows and 6 columns, and the clumps label is 3,600 rows and 7 columns. But you can also ask, I mean, in some scenarios, like a fits image may not be necessary. You want, for example, a text file. So you can also change your output. I just changed the catalog from fits to text. And you see, when I run it, now I have 2, because, you know, a fits file can have multiple extensions, but a text file can't. So that's why when I done this, now I have 2 text files, one catalog O and one catalog C. So this is for clumps, this is for objects. And now I can use basic, command line things, because this is standard plain text, ASCII. So you can just like look at the clumps catalog, and here you go. You see, these are all the columns that we requested. If I just show you the command again, you see the ID, the RA, the DEC, the magnitude, the signal to noise, the access ratio. You see them all over here. And okay, but there's one, just let me, so over here, I'll just explain a little about what's the difference between fits and text. So when you, well, let's have a look. So we can do ls minus lh, which Carlos explained in the first session, and star.txt and catalog.fits, right? So have a look here. This catalog.c is 253 kilobytes. Catalog O is 144 kilobytes. But catalog.fits that has both of them is only 217. It's like half of the sum of the two, right? So it's taken less space because it's binary format, and it can actually store with much better precision than plain text. And it's faster to read, it's faster to write, it's faster to, it's smaller. So generally, if you want to work with catalogs, it's much better to store them in fits format. Fits is a wonderful format. To actually store the catalogs in this format, it will save you space and be faster to read and write. Okay, so we'll continue with the fits format, and we'll remove the text files here. So let's have a look again. Yes, we have the catalog.fits, and we're ready to look into it, right? Okay, so you want AST table, and well, AST table is Gnuastro's program for playing with catalogs. So you say catalog.fits, and when you press enter, you see you have all of this information for all of the columns. But this is, this is already 2,200 rows. But remember before in the last session, we had to select, the metadata from the lines with the starting with the comments, and like that's just too much, right? Over here, because it's fits, we actually have a lot of advantages. So, AST table has this option info. Right? When you give info, look, it doesn't print the column information, the data, it prints the metadata. So it prints the ID of the name of the column, the units of the column, the data type of the column, and the identity, like the comment describing the column. Now, some tables may not have this. So then, for example, you can see exactly what columns this table contains. So say, for example, so there's also an easy way to do this with -I, it's the same. It's a short version of the info. And then, okay, so say, for example, you just want the RA deck. You don't want the whole thing. Like, for some higher level analysis, you just want RA deck. You do column is RA and column is deck. You see, you just print the RA deck. And there's ways to make life easier. You can just say -C instead of column. It's much easier to type. And you see, again, it's identical to before. And even if you don't want to type the -C, you can just put a comma between them. And again, it's the same. So you can ask for any other column. You can ask for also magnitude. And you see, you also have the magnitude column. And this is how, even when catalogs have like hundreds of columns, you can just select the ones that you want really nicely. But this was with names. You can also use them in, for example, numbers. You can say, column 3 or column 4. And it's just going to, change. You can also give numbers instead of names. And the names aren't case sensitive. This is a fit standard. It's not Gnuastro. In the fit standard, there's no difference between case. So it doesn't matter if you uppercase it or not. Okay, and you can save these catalogs, these subcatalogs. Let's say you have this large catalog and you want to save its output into a subcatalog. So you just like all the other Gnuastro programs, you say -O for output, and you say like my subcatalog dot fits, right? And you press enter, and instead of printing on the command line, this subcatalog is now, if I do AST fits first, subcatalog dot fits, you see it has the single table extension here, and it has the 3 columns that I want, and I can use AST table subcatalog dot fits -I to actually see, you see the columns. I just saved this into a new file that I can play with. So there's many options. So for example, you want to sort your catalog based on some column. So you say -sort, and you say the column you want. So let's say I want to sort by magnitude. There you go. You see, look at the 4th column. This is the magnitude. You see that the faintest object, well, the highest, the largest numerical number for the magnitude is 32.92. And well, you see the signal to noise is like crazy low, but well, anyway, this is like just the sorting. So you can easily, sort all the columns based on any, sort the whole table based on any data that you want. And you can also use the head option to specify, just like the top 5. For example, you see the brightest object is 17 magnitudes, and the first 5 things are here. And so you can also specify ranges. For example, say I want only objects that have a magnitude between 26 and 27, right? So this is how I say it. Look, only objects with the magnitude between 26 and 27 are printed. And I can ask for multiple ranges. So I can say, okay, magnitude between 26 and 27, and access ratio between 0.9 and 1. Like say, for example, this is a crude way to find stars, very crude. But you see, now I have found what can be a first set of candidates of the stars in this field that are roughly circular. And I can even make it like constrain it more, like say 95. Okay, there's nothing like 95. Let's say 92. Okay, so you see these objects have an access ratio of like 93 and above. So these are like probably can be the first candidates for the stars in this field with this magnitude range. And so on. So for example, now you want to count them. Remember the WC command from before? You see there's like 9 stars, 9 objects having these conditions. And you're not just limited to using the table values. You can actually play with them. You can do arithmetic with them. So say, for example, you want, well, you say, okay, remember before to get the magnitude column, we would just do magnitude. We would just get the magnitude column. Okay, now we can actually put this in a single quotate, and then we can put an arith behind it and say, okay, multiply the magnitude column, for example, by 0.01 and multiply, right? And look, you can just play with the columns here, and you can actually, now in this scenario, we don't have too much, it doesn't make much sense, but you can even multiply the columns with each other. You can now this is crazy, but in the general scenario, like if I want to multiply the magnitude column with the access ratio column, for example, here you go. You can just multiply the columns. There's many operators. So if you do info AST arithmetic, this is the program that is in charge of the arithmetic. There's many operators that you can use both in images and catalogs. You see, I'm just flipping through them here. Many things that, you can do. Essentially, you can do almost do a large portion of your, data crunching here. And as you see, it's super fast. You don't need to write like 20 Python lines to import NumPy, import AstroPy, import this, import that, and then load this, load that. No, you just go on. It's just so easy. Okay, and you can also ask for the columns in instead of the names. You can just give the position of the columns. You can say multiply column 1 by column 2. For example, column 1, multiply it by column 2, or subtract it from column 2. You see, it's all it's really versatile, and you can play a lot with it. So then there's another really nice program which happens a lot in the sciences. So you, like, say, for example, we generated this catalog of mine here, and I want to now match it with the catalog of the previous SMAC. Remember, in that SMAC, we just used the catalog from the UV-UDF survey. And for that, let's see, where do I have? Yes, the links are here. This is the notes. This is the lecture notes, which you can also go and pick up exactly what we're following here. So I'm just going to copy this curl command because it's a long URL. It's easier to just copy it here. And I'm going to download it's exactly the same catalog that we used before. So this is the catalog from the creators of the UV-UDF survey. Which added some UV bands to the XDF survey of the Hubble Extreme Deep Field. Okay, so now we have it. You see, catalog UV-UDF is the catalog of those guys. So I just do AST table and catalog UV. So this is a new catalog, right? Say, for example, you just downloaded it and you really don't know what's inside it. So you do a -I, just like we saw before. And when you do -I, you see all of the column information is here. Now you see these guys didn't actually put any comments to describe what the columns are. Yeah, you see, like, it has 97 columns and, like, colors for all of these magnitudes, for all of these filters. Okay, so this is one catalog. And now we saw, like, for example, if I just want the see what was the ID, like the ID and the magnitude F775, I want the CID and the mag F775W. You see, I just asked these two columns. Of 97 columns, I just got these two. And it's so convenient when you're dealing with catalog. Okay, now we want to match these catalogs. So we want to see how many objects we found that weren't in that catalog, and maybe the opposite. Now over here, we don't have too much time, so I'm going to just go with one side of this comparison. So there's another really cool program in Gnuastro, AST match. So that's the job, is to match catalogs. So you have, in this scenario, we've done our own detection, they've done their detection. Now I want to see which one of my objects correspond to which one of theirs. So I say catalog.fix, this is my catalog, right? And then I say, okay, I want to match my columns, my clumps extension. And then the catalog of the, for example, the UV-UDF, I give that. And I say, okay, in this catalog, well, this one only has one extension. So it's almost redundant, but just to be clear, I'm putting it here. Okay, then I have to specify the coordinate column. So C column means coordinate column. So from the first catalog, I want to match RA deck. And then for the second column, for the second table, it's also called RA deck. But generally different catalogs have different names. So that's why these two are different. And then in what aperture do I want to match them? I want to match them in 1 arcsecond, for example. So 1 divided by 3,600 degrees, which is the units of RA deck. Okay, then I want to put my output in catalog matched, for example, matched.fits. Okay, there you go, and finished. You look, it found everything that was in the clumps catalog, and it found 1,822 matches between the two, and now we can actually look at these things. So we can actually say AST fits, and okay, AST fits and catalog matched. And there you go. You see, you have the input catalog and you have the output catalog. Well, the reason is that this is a small field compared to, because their original catalog is much larger and a much larger field. So as I showed at the start, the region of this, you see this is from this region, this huge region, and then the abyss survey is only this deep part of it. Okay, so yeah, so now we have the two catalogs here, and you can just look at them as with any other catalog. And now, but the good thing is that that the rows are matched, because look, the number of rows are the same. So now you know that these are the same, are exactly the same objects. And yeah, so okay, then there's some nice things you can do. For example, you can let's see, you can do, there's another really nice program. Okay, so you've made your catalogs, you've made your tables, you've analyzed your tables, you've matched your tables. Now, for example, you want to get a statistics of the columns, right? So for example, there's another really nice program in Gnuastro, AST statistics. So you say AST statistics catalog.fits, and you say, okay, which column do you want from catalog.fits? I want the magnitude column. Magnitude column. Okay, look, this is the distribution. Isn't this cool? Like, isn't this cute, tiny ASCII histogram? It took me like one day to write it, but it's like, yeah, it's really cool, because when you're like on a big computer and you don't have this graphic user interface, and you just want it, you don't want detailed, like beautiful plots. You just want to get a sense of what's the distribution of the magnitude, or for example, the distribution of the axis ratios. This is perfect for that. And look how, you know, how easy and how fast it is. So it actually prints some basic information about the statistics of the data set. Then it also for the particular column. And you don't need a fancy graphic user interface. You can do this with SSH with no graphic user interface. But you know, it just gives you a sense of what the data feels like. For example, and it's not just limited to catalogs. You can also run AST statistics on the images. So for example, remember the only sky image that Raúl made? He masked all the detections, right? So now, for example, we want to check that the masking of the detections, only the noise was left. So let's have a look, and let's just see the distribution of the noise pixels. So we run only sky, and look, it done it. This was like a 3000 by 3000 pixel image in floating point. And look, it done it so fast. Yeah, this is one of the great advantages of Gnuastro. And look, you didn't spend any time in writing a program, import this, import that, you know, load this, load that, go do this, do that. No, you just run it here, and you get the statistics. And okay, you don't have to even, like, you know, these are just some general statistics. You can specify it in more detail. Say, for example, you just want the median. Here, done, finished, right? This is the median of the sky level of the noise, only the noise pixels in the noise chisel image. And you see, you can, it actually gives you a lot of flexibility to play with your data sets. Okay, now we can actually, let's see. Yes, I'm just looking, what's the next, okay, so with AST match, we can now, so now we have we can also, as you saw, well, the output was AST fits catalog matched. And this catalog only had, you know, 2 extensions. So the tables are still different. But there's this other option. So I can use Control R, you know, as Joseph explained in the last session. If I just do Control R and AST match, it actually shows my last command. So, you know, use this a lot. It's a wonderful command to bring up the history. So this was my old AST match command, right? I go to the end and I say, okay, instead of making 2 catalogs, merge the columns of the match thing. So I can say outcols. It means the output columns, and from the first catalog, we started with A, like keep the ID, or keep column 1, and then from the first catalog again keep the RA, from the first catalog keep dec, from the first catalog keep, for example, magnitude, but from the second catalog, so the second catalog goes with B, keep the magnitude F160W, which is the image we were using. Look, when I run this, the number of match things, well, of course, is the same, but the output is now not 2 catalogs, but 1 catalog. Catalog matched, you see, it's just 1 table. And then if I look with AST table inside the metadata of this file, so catalog matched, and I do, yeah, AST table catalog match -I, you see, it actually kept these 3 columns from the first match, and then these ones, this catalog, this actually came from the UV-EDF catalog. Now it's in 1 table. So for example, now with the column arithmetic that I had before, I can actually, like, for example, calculate the difference in magnitudes. I do an arith here and I say magnitude and mag F160W, subtract them. Here you see the difference in magnitudes are now visible here. here. And if you want to actually see the distribution, you just type this to AST statistics and you get the distribution. Now there's a few outliers because they use -99 for blank things, which is really bad. So you can say greater than, greater equal to like, well, -2, for example. And look, you can see the distribution of the, let's make it -3. So ignore everything behind it, or -4. Well, let's say -10. Okay, yeah, you see, you can actually get the difference between the two catalogs, the magnitudes of the two. You see how many things you can do with this? You can play with the columns a lot. You can do a lot of arithmetic with the columns and get some nice results. Okay, so finally, I'm wondering if this step can take a little too long. So if we have time in the end, I'll go to the last step where I want to actually match objects and show some objects that didn't match with the UVF catalog. But just to make sure I don't pass my time, I'll stop here and I'll give control to Joseph. And in the end, if we have time, I'll continue. But the guide already has everything you want. So the lecture notes that were up here, you can always look here and follow exactly the commands that we run. Oh, and finally, before I finish, I'll just do, so all of the programs have a cite option because look, this is a scientific software. Please cite your software, right? In your papers. You know, people like me, the people that wrote your software, they need citation to, you know, find a job, right? So yeah, so like in the case of Gnuastro, I've really made the job easy for you. You just do --cite, and look, it actually puts the BibTeX entry of the papers that you should cite for each program. And it actually even gives you an ASCII flower as well. You see, this is a nice flower. It says, yeah, many thanks for citing the Gnuastro, and acknowledge it also. Like we've, you know, people who use Gnuastro should mention that like we got funding from the Spanish government and so on. Yeah, so please have this in mind as well. And different programs can differ. For example, AST MENK catalog, we're writing like different papers for the different programs. Yeah, so have these in mind as well. Okay, so I'll stop here and I'll give control to Joseph. Thank you very much.
Thank you, Mohammad. Everyone hear me?
Yes.
Okay. All right, let me share screen. Okay. So hi, everyone. I'm a student at the IC under Jorge and Casiana studying XMPs. And for my part of the talk, I'm going to be doing a demonstration using one of my galaxies, the one shown here. So Gnuastro has been enormously useful for me, who wants to study the photometric properties of XMPs, particularly the diffuse light that you can sort of see in this image. But the main purpose of my part of the talk is to ultimately show how noise chisel does an excellent job at revealing light that you wouldn't at all see by eye. So for some of my commands to save time, I'm going to copy and paste. Also, there are some cases where the commands aren't ones I use all the time. So the first thing we want to do is well, I'll summarize my part of the talk. I'm going to download the GR and I bands of the galaxy you just saw and align each of them with the celestial coordinates using warp. Then I'm going to make small crops of each filter and make an RGB mugshot using table crop and convert type. Then I'm going to make bigger crops to make a deep image using crop and arithmetic that will feed to noise chisel. And then with noise chisel, we'll reveal the deep extent of the diffuse component of the demo XMP galaxy. So to start off, we're going to get the image, which is at this URL, and I make a variable f because the URL is the same for all the filters. And I use the wget command to download them. And then I decompress them with bzip2. And we then rename them with just the name of the filter .fits. So let's keep going. So it's downloading G image. and now R, and now I. And lo and behold, here we have GR and I. So this is nothing to do with Gnuastro so far. This is just Bash. But if you're not comfortable with Bash, the more comfortable you are with Bash, the more useful the more power you will have while you use Gnuastro. So let's see what's inside one of these images. There are 4 extensions. The first is a 2D image, and we have a 1D image, and then 2 tables. So that's interesting. Did you know that in the most popular database in each image, there's actually a lot more information there. Let's just take a quick look, find our galaxy. It's over here. Okay. So now we're going to use warp, and we need to use it on all of the filters. So we're going to use a loop again, but for now, just do it on 1. So I called a variable f and stored it to G. And remember, the 2D image is in the 0 extension. And we're going to align with the celestial coordinates and give it a name, $f align fits. Okay, and let's compare before and after. So on the left, it's the original image. On the right, we have the image now aligned with the celestial coordinates. You can see east and north in the first image is not in the standard place, but now it is, as you can see up here. So now let's repeat that for all the filters. I just jumped to the beginning of the last command with Control A and GRI, and we need to jump to the end with Control E, and we're done. And I have the issue here. I forgot do. So do if you work. Okay. All right, and we have our 3 aligned images. Perfect. So let's move on to making RGB mugshot image. In this part, we're going to demonstrate how we can use an operator where we convert the WCS to image coordinates so that we can then crop in image mode. So we're going to store the RA index into variables. So I can repeat this for all of my galaxies now using the same commands by just updating the RA index. And I haven't actually used this table column arithmetic before, so I'm going to cheat a little bit. So we now have image coordinates from the WCS, and we need to format this for crop. So we're going to do the same thing, but now pipe it to awk like so. And now it's in the format that crop needs, and we're going to store it as a variable. It's called center equals $ parentheses and echo $center. Great. Now we can use crop. So let's demonstrate on the G. We're going to use image mode on G. We're going to have it be a square, 300 pixels across. The center parameter is set to the center variable. We're using the aligned, and we're going to call this G small fits. Great. And let's take a quick look at the result to make sure it's what we expect, and indeed it is. So let's repeat that for the other filters. I'm going to just go ahead and copy the loop. So we're doing it for GR9. We're updating the center because the image coordinate center of the galaxy will be a little different in each filter, and then we're cropping. So let's go. And great. Let's make sure everything looks as we expect. We're going to write the images here in the order of RGB so that we can be prepared for making the RGB image. And we're going to display everything in one row by tiling by columns. So good. We are all set to make the RGB image. Okay, so we do that with convert type. AST convert, and there's two T's at the end for convert type, but I told you I'm going to use the last command to get rid of DS9, AST convert type, and go to the end. All of the extensions are now 1, which is the standard. TSS, for some reason, doesn't have the 2D image in the standard place. So if we call this output equals RGB.jpg, let's take a quick look. We don't see anything because we haven't adjusted the high and low flux parameters in the display. So let's add those. The images are already sky subtracted, so flux low we're going to set to near 0, and flux high. The units of the pixels are nanobags, which are small. So flux high we'll use 1.5 for now, and very nice. You can see how fast you can do really useful things. You can save this as an EPS for your paper and do it on in an infinite number of however many sources you have RA in deck for. So great. Part 3 is the simplest part, where we're just going to reuse the same thing we just did, but change the width, because we need a big image that we're going to, we need more field for noise chisel to evaluate the noise properties, and we need to update. So we're changing width from 300 to 1300, and we'll now call the output big. Okay, and yeah, so I was saying that we need to have, it's ideally, noise chisel will reveal the deep light in the XMP, and even more so if you have a deep image. So we're going to average the 3 bigger crops, and we'll do that with arithmetic like so. I big, R big, G big, and 3 identifies the number of input images. We're going to take the mean. The abbreviation for the global HDU is -G, and we'll call this deep.fits. Okay, so I'll now display everything to make sure it is what we expect. And we have the I, G, or R, G, and then deep in that order. I'm going to show everything with the same limits. And we see that I is the noisiest, G is the least noisiest, but the galaxy is, and most of the diffuse light is brighter in the redder bands. So in the end, we have the advantage of the lower noise in G and the brighter host emission in red. So the signal to noise of the host is best, and then the average, which is useful as we move on to noise chisel. So AST noise chisel, deep black fits, and we'll call this, as Raúl did, okay. Now ES9. Note how fast everything is. Mohammad said that, people who are once using a supercomputer to do something that took days just took a few minutes with his software, and their minds were blown. Let's check the output of noise chisel. So here we see the detection map. Let's zoom in on it and bounce back and forth. And already you can see how the detection of the galaxy is much larger than what you can see by eye. And just to emphasize, or to discuss this point further, we're going to make a signal to noise image using arithmetic, where we divide deep.fits by the last extension in the noise chisel output, which is the sky standard deviation, and we'll call this output SN.fit. And now we can simply use arithmetic again to mask all the pixels fainter than a signal to noise of 1. So we do 1 greater than, and we'll call this output SN with a threshold of 1.fits, and let's take a look. So each pixel in black has a signal to noise above 1, and the white is below 1. Now let's look at that along with the other images in question. So we're going to pull up the detection map, which is in the second extension of the noise chisel output, and let's compare that with the image we just made, and show everything in one row. Okay, so what we're going to do now is evaluate the statistics near the edge of the detection to demonstrate that indeed there's a lot of signal there. So I'm going to make a region just inside the detection, like so. Now I'm going to copy it over here where you hardly, don't think a betting person would say that, there's an object there, and I'll copy it over here too. And let's pull up the statistics in this region. Okay, so you see the sum is more than 13, and let's compare that to a region where I'll change this color. Let's call this blue, and we'll copy it where we know there's no signal, and we'll copy it over here, and we'll pull up the statistics here and compare. And we are actually less than 0. And if we move this around somewhere else, like in the lower left, there's no signal, and now we're slightly above 0. So indeed, there's lots of signal in this region. And we look on the far right, and most of the pixels are white, signal to noise below 1. But if you look at the error here, around 4, and the sum, so this region as a whole has a signal to noise of about 4, even though most of the pixels are actually have a signal to noise less than 1. So as you can see, noise chisel, with just using the default parameters, has done an excellent job revealing the deep extent of this XMP galaxy. And that's the end of my portion of the talk. what I would normally do, you know, in my work is then move on to segment, because I'm also interested in the clumps, and make catalog where I can get the initial analysis of the clumps and the diffuse region. And I will end by just saying that I know you've now seen a lot in just the last hour, but please have a look at the tutorials, stop your research for a few months or even a year, learn Gnuastro, you won't regret it. It's been enormously useful for me. I went from being kind of bored in my PhD to now thinking I have no choice but to show the world what I can do that no one else has done before. I guarantee you I've used segments more than anyone else has. So please, you know, part of the purpose of these talks is so Mohammad can not have to repeat himself. You know, he gave me so much help, and I can't thank him enough. But now, you know, you can, hopefully he has less work. If you have questions about segment or make catalog, feel free to come to me. So thank you very much.
Thank you very much, Joseph. Thank you. So Carlos, I think we can finish now. It's up to you. Should we have questions or?
Yeah, I think so. I mean, this ends the formal seminar, but I think we should allow for some questions.
Should I stop sharing?
Yes, yes. Thank you so much, Joseph. It was great.
Yeah. Yeah, this was a very nice scroll through all of the capabilities that the package has. One of the most beautiful things I think is that everything can be scripted, right? So it's very easy to repeat everything. You don't have to retype stuff. You just put it into a file, make a script, and then if you want to repeat things, changing a parameter, you just do it again. Let's go to questions. Anyone interested in doing questions, they can just say something in the chat, and then I'll give them the word. Well, meanwhile, one question I had, it was regarding the timings, right? The speed. It was obvious from the messages in the printouts of some of the codes that they are multi-threaded, right? So you can they can use really all of the cores in the machine to speed up the calculations.
Yes.
But yeah, there are some other tools that can do similar things, right? For example, cross-matching catalogs for coordinates on the sky is something that I always use, for which I always use TopCat. Have you done any comparison between the timings, for example, for TopCat or Gnuastro?
Timings, TopCat, no. With timings with TopCat, no. Timings, no. We haven't compared the timings of the catalog matching. Yeah, but the thing is that TopCat, because it's a graphic user interface, it can also be command line scripted, but ultimately uses the same engine, and it goes into a virtual machine, you know, the Java virtual machine. So it's I'm really curious. In fact, now that you mentioned it, there are so many packages, and we only touched on some of them. So yeah, it would be interesting if someone's interested to do the test.
Yeah, I think even myself would be happy to do that.
Great. Yeah. We'd be happy to help.
Yeah, I don't see any other questions here in the chat, but maybe people that are connected through Zoom want to simply speak up.
Hi, Carlos.
Hi.
I'm enjoying a lot these talks. Let's say that I would like to see if maybe it's a good idea to have a kind of course, or I mean, to understand all the power of the system, right? You probably can do much more than what we see in the last two talks. I mean, I learned some things, in the first talk, some others this one, and maybe we should think in a short course on how to deal and reduce data and things like that with this package. So thinking in, I mean, dinosaurs like me that are still using IRAF and things like that will like very much to move to something that is going to survive, right?
Yeah, absolutely. I mean, Mohammad can say more. That's the absolute purpose of this series, to get people excited about these tools that exist and most of us are not aware of. And Mohammad has been thinking about expanding these, following up this with a longer course, right?
Exactly. Yeah. So there is, in the tutorials of the manual, there's like, I think it's almost 50, 60 pages. So it goes really deep into everything. And what we've done so far is that in several workshops, I think so far we've had 4 or 5 workshops in different places, from Switzerland to France to India. And we were planning one here, but because of the virus, it was canceled. So that tutorial, essentially the coursework for such a lecture is already done. The tutorial is there, it's already online. So effectively what we do, people just come and run those on their computer. And well, always the questions come up, discussions come up as they're trying it. And we're there to help. Yeah, we have such a thing, and organizing it won't be much hard because all the hard work has been done over like 3-4 years of writing that manual. So yeah, it's very cheap in terms of time for us to organize such a thing. We'd be very happy to do that. Unfortunately, the number of Gnuastro users are increasing a lot in IAC. So it's not just me, as you saw. Raúl and Joseph are now very nicely professionals as well. And yeah, and many more. Yeah, Marcel from your team has also really become a master. I saw him a few times using it, and he's doing a great job. Yeah.
Is there any other questions that people want to formulate themselves? Okay, if not, then we'll leave it here. Thank you all for coming. Thank you, the speakers, for the excellent talk. And we'll continue in a month or a few weeks' time with the next talk of the series. I think there is another one coming up on the shell, on the PowerShell tools for the shell. And there will also be another one on Git, right? All right, thanks very much.
Thank you very much, everyone.
Okay, bye. Keep safe.